Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk, but if you have questions, unmute yourself and ask questions, or we can wait until the end to the Q&A sessions. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Ching Yao Lai, who is an assistant professor in the Department of Geophysics and an affiliated faculty of the Institute for Computational and Mathematical Engineering, so-called ICME, at Stanford. Before joining Stanford, she was an assistant professor at Princeton University. She received an undergraduate degree, 2013, in physics from National Taiwan University and a PhD in mechanical and aerospace engineering from Princeton University. She completed her postdoctoral research in geophysics at Lamont Earth Observatory at Columbia University, where she received the Lamont Postdoctoral Fellowship. Her current research focuses on enhancing the representation of machine learning models to tackle multiscale problems. She was the recipient of the 2023 Google Research Scholar Award and 2024 Sloan Research Fellowship. Today, Yao will talk about machine precision neural networks for multiscale dynamics. I'm sure we are going to hear a wonderful talk from her. But before I pass the baton to Yao, as a tradition to the DDPS seminar, let me ask a question, somewhat informal questions to her to get to know her about somewhat outside of her technical reason. All right. So I happen to know that you like to travel. If you can share the most favorite places you have visited so far and share with us why you think so.
Yeah, first of all, thank you, Yongsu, for the warm introduction and invitation. I was not expecting that question. I guess the travel, I really enjoy my travel in Europe in particular, just because I've learned about it in history in my childhood, and it was just wonderful to see historical buildings. You also just distract myself from the daily routine, so that's the part I really enjoy. I don't know if this is sufficient.
Awesome. Yeah, there's no correct answer here. So thank you so much for sharing your traveling experience.
Yeah.
All right, the stage is yours.
Okay, yeah. So yeah, I'm excited to give the talk today, and today I'll talk about the work in my group. My group has been developing recently to enhance the representation accuracy of neural networks. I hope I can convince you that it is kind of problematic that vanilla neural networks suffer to represent multi-scale data, which motivate us to develop machine precision neural networks. And this work that we discussed today was also published in Journal of Computational Physics and Physical Review Letters. Next slide. All right. So there has been an emerging trend of research using machine learning models to emulate numerical simulations to substantially reduce its computational cost. And success stories include the recent bloom of machine learning-based weather forecast models. A classical numerical weather forecast prediction is made by numerically solving coupled partial differential equations that describe the evolution of states, and that's denoted by Z here. And in the ML emulator, a physics-free machine learning model is used to approximate the dynamics that is denoted by F here, which describe the time derivative of the states. So the machine learning model will take the states at the previous time as input and then predict the state at the next time as output. This approach is very successful, and after training with the ER5 weather reanalysis data, DeepMind has shown that they're able to use the a graph neural network to take the states in the current time step and predict the next time step, and then take the next time step result to predict the next time step, and so on. So they show that this can make 10-day weather forecast with precision that is comparable to the state-of-the-art physics-based numerical weather prediction model. And this takes a lot of time to train, but once it is trained, it takes negligible amount of time to make predictions. So this is just another example and image of the neural network represented global wind field from one of the recent machine learning weather forecast model. And here, if you compare with the ground truth training data from numerical weather prediction, you can see that the machine learning based weather forecast can well capture the large scale feature, right? So these two wind fields are almost indistinguishable, but the ML based model is missing a lot of the fine scale high frequency details that's present in the numerical data. And it's even more evident in this plot. So here is the spectrum of the wind field. The horizontal axis is the wave number. The vertical axis is the power density. The black line is the spectrum from Euler 5 data, and the colored lines are the spectrum from various different machine learning-based weather prediction model. So you can see that most of the ML-based model capture the spectrum at low wave number because they capture the large-scale features. However, they deviate from the spectrum for higher wave number, so it's missing all the fine-scale, high-frequency details. And this is even more severe when you look at the prediction at day 10. So at day 10, a lot the mismatch between the ML-based model and the ground truth happens at even lower wave numbers. Whoops. I think, sorry. Are you still seeing my screen?
No, screen is gone now. Somehow.
Sorry, let me reshare again. I don't know what happened. Share screen.
Take your time.
Window. All right.
Yeah, the first page we are seeing. Yeah.
Okay, so let me go back to the slides. Yeah. Okay, so what I just described is related to the so-called spectral bias of the neural network. Spectral bias refer to neural networks' tendency to prioritize fitting functions with a certain frequency range. As demonstrated in this 2019 paper, I really like this figure. I think it's really clear. So here the blue line is the target function, and the green curve is the neural network prediction over iterations. So you can see that the neural network can first fit the low frequency function, but then it takes a lot longer to fit the high frequency signals in the target function. And this is bad news because problems in the physical sciences often exhibit multi-scale features, and neural networks are used because of its property as a universal function approximator. However, in practice, neural networks often fail to capture fine-scale details due to its spectral bias. So a popular solution is the so-called Fourier feature, and this was proposed in Tensik et al. 2020 paper. This Fourier feature is composed of basis functions of cosine and sines, and it maps the input coordinate of the multi-layer perceptron into this feature before passing the information into the hidden layers of the neural network. And the intuition is that you can give some hints to the neural network that there exists a range of frequencies that are relevant to represent the data. So you can see here that this is the original image represented by the regular neural network. It looks kind of blurry, just like what we saw earlier. But after applying the Fourier features, now the neural network capture all the accurate details in the image. Okay, so that was spectral bias, and now there's another additional challenge of machine learning emulators. So this is one of the machine learning-based emulator, ForecastNet, and this is prediction out to 30 days. You can see that the errors start to accumulate, and then the temperature field just, we call it blow up over time. And because just recall that in this case, neural network is used to approximate the time derivatives of the states, the dynamics. So if the neural network have spectral bias, it could cause errors of approximating the states at smaller scales, and this error can be propagated in times and therefore make long-term prediction terribly inaccurate. So spectral bias could be one of the reasons that can cause the blow-up behavior we see in emulators. So to summarize, the big questions that I want to discuss today is strategies that can tackle spectral bias of the neural network. And another question is, how can we make the neural network approximation as accurate as possible? So this is today's outline. I'll first talk about an algorithm our group developed that can push the error down to machine precision and tackle the spectral bias. And I'll talk about the extension for problems related to PDEs, and this is still preliminary and ongoing work. And finally, I'll talk about some challenges and promises in this area. So, okay, so expressiveness of neural network. Here, my postdoc, Yangji, he used a vanilla neural network to fit a 1D function. So here he's just a silly analytical function that we try to fit. And the y-axis is the output, neural network output, the x-axis is the neural network input. The blue line is the function we're trying to fit. The dash red is the neural network prediction. So here the loss function quantifies the difference between the ground truth function and the neural network prediction. And you can see that with a regular neural network, the error can go down to about 10 to the minus 5. But the question is why does the error not get lower when we train for longer iterations? So here we try increasing the depth of the neural network, increasing the width. We were always seeing a saturation of error like this. So the question is what's the minimum error we can push the error down to? Neural network if neural network are truly universal function approximators, it should not have this. It can correspond to, it should be able to achieve arbitrarily small error, theoretically. So here we propose the multi-stage neural network that use a subsequent neural network to effectively learn to correct for the errors from the first neural network. And this multi-stage neural network can achieve much better precision with less number of total neural network parameters and less computational cost compared to a single neural network. Whoop. I don't know why this is happening, but let's go back. Okay, so before going into the detail of the algorithm, I want to draw your attention to this very simple explanation of the spectral bias. So here, this is the expression of a single layer neural network with input X and output U. Here, the W and B's are the neural network parameters. And here, the loss function quantifies the mean square error between the neural network output and the ground truth. So here we denote the Fourier transform of the function as a U hat. And the loss function can also be written in as the Fourier transform of the neural network prediction. So if we will skip the derivation here, but it can be shown that the gradient of so during gradient descent, we know that the loss function is updated based on the gradient of the loss function with respect to the neural network parameters. It can be shown that the gradient of the loss function decay exponentially with higher frequencies. And this is important because it shows that the gradients become very small for larger k, and therefore it would take extremely long number of iterations to learn the high frequency functions. And this is a simple explanation for the origin of neural networks spectral bias. So to mitigate this problem, it's important to rescale the neural network weights. Note that in this expression, the exponential decay, in this decay, it is this factor, the frequency divided by W that determine the decay, and W is the neural network weight. So if we can increase the neural network weights proportionally with the frequency k that we want to capture, we can keep this gradient large for larger k, and this can reactivate the learning of high frequency functions. So here in our implementation, we have a scaling factor called kappa, and that's a multiplier in front of the weights of the neural network that connects the input to the first hidden layer. And note that this is similar to the Fourier feature implementation, but here we don't include the cosine activation function because that's not necessary. So the kappa is a user-defined parameter. You can set the value. Large kappa has the effect of rescaling the input x and make it easier to learn high-frequency functions. So we can see that with large kappa, the neural network approximation can fit the target function better. And this was also shown by this paper by JTAC in 2020. In the case when kappa is smaller, it's really struggling to fit the target function. So, however, we are still, even though we increase the kappa, you're seeing we're still missing part of the target function. So here we change the activation function from hyperbolic tangent to sine, and it shows that the fitting is much better. Therefore, a combination of large scaling factor and the sinusoidal activation function gives much better error. And we know that this implementation has a similar training error compared to the Fourier feature net. So one thing to be careful with is that the network can start to overfit the data if you increase the kappa further. So here we can see that if you just look at the training loss, when you increase the scaling factor, you can keep minimizing the loss. So here the kappa is like up to 300. The loss looks very small. However, this is actually quite deceiving because if you look at the actual prediction of the neural network with larger kappa value on the higher resolution grid point, you're seeing that it's actually overfitting the function and have all these wiggles. So it's important to know that there's actually a optimal range of kappa that works well. Here we show the root mean square error of the neural network as a function of the scaling factor kappa, and you can see that the optimal kappa is related to the dominant frequency in a target function, which is denoted by FD, and this is aligned with our expectation from the spectral bias analysis. I don't know what happened. Let's keep. This is okay. It's somehow like skipping many slides. I'll go back where we are. Okay, here's good. Yeah. All right. So that was for fitting high frequency functions. Now we have another issue, independent issue to overcome. So when the neural network training error is very small, we know that the learning becomes very slow, right? And so here is the main idea of the multi-stage neural network. Inspired by perturbation theory, here we write the neural network approximative function as a superposition of the leading order approximation U0 and the higher order error terms like U1, U2, etc. So here epsilon 1 is a small constant, and epsilon is much smaller compared to epsilon 1. The U0, U1, U2, etc. are the neural networks from different stages. So although the first neural network U0 doesn't perfectly fit the target function, we can use a subsequent neural network U1 to learn to correct for the residue from the previous neural network. And because here the U0, U1, U2 are all orders of magnitude 1 functions, so it's easy for neural network to capture all these error terms instead of having a single neural network capturing all the small magnitude details. And note that here's a list of related work with similar strategies. So sequential residue learning and multi-layer neural networks. This paper actually is also able to get the error down to machine precision. There's also the stack networks by Howard et al. And precision machine learning. So this is really, I think, a rising trend of research to try to understand what control the error of the neural network approximation. Okay, so here is a numerical demonstration. This is another 1D target function we are trying to fit. And so here show after one single neural network the error of the first neural network. So the magnitude is about 10 to the minus 4. The x-axis is the input of the neural network. So we do a Fourier transform of these error and look at it in a frequency space. So here you can see the dominant frequency corresponding to the error of this first neural network. And then we use a second neural network, a subsequent neural network, to learn to fit the error from the first neural network. So now the second neural network with the first one altogether has an error that's much smaller, so about 10 to the minus 8. And one thing that's interesting is if you look at the frequency of this error of the second neural network, it's actually much higher. So we can look at the frequency error in the Fourier space. It corresponds to a higher dominant frequency. And then we can repeat this procedure. We use the third neural network to learn to approximate the error from the second neural network. And now the residual of the three networks combined become 10 to the minus 11. And the same story, after all the networks are stacked together, we can achieve the error that's close to 10 to the minus 13. And now the error has a really, really high frequency. So here is just to show the error of the approximation throughout iterations. You can see that the error convergence for this multi-staging training scheme is a lot faster with training iterations compared to a single neural network. And this just shows that throughout different stages, the error of the approximation gets lower. At the same time, the dominant frequency of the error increase. And this actually, we see that it follows a power law with exponent 1/6. This exponent is actually quite universal. We see this for various different target function that we have tried, and is relatively unchanged with different sampling data and different different architecture, different number of layers, number of units. I'd love to, if you have ideas of how to explain this exponent, I would love to chat more about it. Okay, so that was for very simple, right? Like 1D, learning 1D function. And here we want to see if we can use this idea to learn 2D data, like the data of a flow field. So here my student Jenkins, she used the spectral methods to create the numerical simulation that solves this 2D incompressible Navier-Stokes equation with Reynolds number 2000. And here is the vorticity field that evolved with time. And here is the energy spectrum. So we like this example because it has the energy spectrum that spans over scales that with 2 orders of magnitude. So it's a simple example of a multi-scale problem. So here, what we want to do is to just use a multi-stage network to fit a snapshot of this flow field. So this is the target function of the flow field at a time. And here is the neural network representation of the data. So the input of a neural network is the coordinate, and the output of a neural network is the string function, the flow field. And you can see that the difference is quite small. This is the error between the target function and the neural network approximation. The magnitude of the error is about 10 to the minus 4. If you look at this error in space, it's quite interesting. It has these wiggles. So we look at this error in Fourier space, and we see that there's some dominant frequency of the error. So here is the spectrum, energy spectrum of the ground truth data shown in black, and the neural network data shown in blue. And you can see the spectral bias. So the neural network captured the small wave number energy spectrum, but has a mismatch in the high wave number region. Okay, so we're going to do the same procedure. Now we will use a second neural network to fit the error from this first neural network. And this is the error after the second neural network. Now it has the magnitude of 10 to the minus 7. And the error of the second neural network now has a higher dominant wave number. And we keep this procedure after the third stage, the error can be down to close to machine precision of the double floating point, 10 to the minus 16. And now has you can see that the energy spectrum, the neural network approximation correspond to an energy spectrum that's aligned really well with the target function. So this is just in comparison, comparing the multi-stage neural network with the regular neural network. We showed that for the energy spectrum, here the red line is the regular neural network. The green line is the multi-stage neural network that can tackle the spectral bias and agrees very well with the target function. We look at the loss convergence compared to the regular single neural network that has a loss value that converges over iterations. With the multi-stage neural network, we can achieve unprecedented accuracy and down to machine precision of the double precision floating point. Okay, so this is a quick summary. So for this data fitting problem, the training data for the higher stage neural network comes from the error from the previous stage. And the error of the higher stage neural network are usually higher frequency functions. So although it is difficult for vanilla neural network to capture high frequency data, we can use a scaling factor kappa that can be determined directly using the dominant frequency of the residues. And this is exciting for us because using this multi-stage neural network, we can tackle the spectral bias and achieve unprecedented accuracy. Okay, let's do that again. So yeah, that was, I want to emphasize that it sounds like there's lots of steps, but actually all of these steps can be automated. Okay, so so far we have talked about machine precision neural network for tackling spectral bias, right? The next question is, can we use this for PDE problems? Can PDE residues also be pushed down to machine precision? So this is a much harder problem to investigate, and this is still ongoing work. In particular, I'll in the next few slides, I'll talk about the application of multi-stage neural network to physics-informed neural networks. So for background information, physics-informed neural network leverage neural networks' expressiveness to approximate solutions to PDEs. And because neural networks are analytical functions, its derivatives and therefore the PDE residues can be calculated exactly using automated differentiation. And a neural network prediction that makes the PDE residue equal to 0 is that will exactly satisfy the equation. So throughout the training process, the neural network will find an approximate representation of the PDE solution by minimizing the loss function that include both the PDE residue and the associated boundary conditions. And I should add that I think physics-informed neural networks are better for solving inverse problems because for forward problems, there are also many other traditional solvers that are much faster than PINNs. And in the next few slides, I will still use forward problem as examples to just to explain how the multi-stage PINN works. But in the end, I will talk about the impact of this approach for an inverse problem. Okay, so before talking about the detail, I want to emphasize again the importance of the scaling factor. So here is the example of the Poisson's equation. And this is a nice example because we know the exact solution. So here is the PINN solution of the vanilla PINN to the Poisson's equation, and it has a prediction error about 10 to the minus 4. Because this solution has high frequency features, I want to just remind you that due to the spectral bias, it's harder for PINN to approximate a solution like this. But what we can do again is to change this scaling factor. So here, if we make the scaling factor that's closer to the dominant frequency in this sourcing term, 6 pi, now we can reduce the error by 2 orders of magnitude just by changing this scaling factor. Okay, so how do we apply multi-stage idea to PINNs? We know that for the previous regression data fitting problem, right? The training data for the higher stage neural network comes from the error of the previous stage, and that can be calculated if you know the target function, if you know the ground truth. But for solving PDEs, we don't know the solution, right? We want to find the solution. So we do not know the target function. So in the case when you don't have any target function, how do we design the higher stage network? What would be the training data? Okay, so I'll explain that in the next few slides. And using this simple example, so here's a simple linear ODE. And again, the residue is just the rewriting the equation here. So this example also is quite nice. It has the exact solution, and we will define the solution error as the difference between neural network predicted solution with this exact solution. Again, this gray colored text here, that's not going to be seen by the neural network. I'm showing here just for validating our result. Okay, so here is the PIN result, PIN prediction compared to the exact solution. And after the first stage. So here is the PD residue as a function of input x. And here we look at the residue in the Fourier domain, so we can see its dominant frequency. Interestingly, here we can calculate the solution error by comparing the red and the blue lines. And then here this is the solution error. We can also look at the solution error in the frequency space. Again, this lower panel in gray here is not seen by the algorithm. I'm just showing here for your information. So one thing interesting we see here is that the dominant frequency of the PD residue is close to the dominant frequency of the error of the solution. Another thing is that the error of the solution, the magnitude of the residue is larger compared to the magnitude of the error of the solution. Okay, so we know that to design a multi-staging neural network, we need to specify the orders of magnitude of the error for the second stage solution, which is this epsilon1 parameter. And the question here is, how do we estimate this magnitude of epsilon1 with the absence of ground truth solution? So here we can plug in this solution NSOC into the original PDE. And by doing so, we can obtain a new PDE where the right-hand side is simply the PDE residue itself from the original equation. So the first neural network's PDE residue can give the PDE for the second stage neural network that solves for the higher stage term U1. And moreover, the magnitude of the dominant term in the left-hand side, in this case, is this first derivative term. This term can be estimated as the magnitude of U1 over the X length scale of U1, which is related to the dominant frequency of U1. So if we want to balance, in this equation, the dominant terms are these two highlighted in blue. By balancing these two dominant terms, we can estimate that the magnitude of the solution error, epsilon1, based on the magnitude of the equation residue and the frequency of the PD residue. So we have all the information that we need to estimate this epsilon1 parameter. Okay. And again, all this procedure can be automated. So now you might ask, works for ODE with first derivative. How about higher order derivatives? For higher order derivatives, you can apply this very similar strategy. So here, instead of estimating term that has like U1 over X, you will have like 1 over X to the power of N, where N is the number of derivatives in this term. Okay, so a natural question is, how about nonlinear equations, right? Here is, we discussed that in our paper as well. Here is a simple example where you have a U-squared term in your PDE. It turns out if you have an equation like this, you can just follow the same procedure. And then when you write down the second stage PDE to train the second stage neural network, you'll see that because the epsilon1 parameter is much smaller than 1, so all these nonlinear terms that involve U1 will fall into a higher order epsilon1 squared term, and this can be generally disregarded. So this suggests that although despite the nonlinearity of the original equation, the governing equation for the higher stage network essentially can become a linear equation. because this term is negligible. Therefore, the similar strategies that I just described would apply here. And here, I'm just mentioning the basic intuitions of our approach. If you want to see more details, you can look at section 3.1.2 in our paper for the formal derivations. Okay, so this is just to show the result. Here we have all we need to conduct the multi-stage training for PINNs. We know that the frequency, so this is the PD we're trying to solve. This is the first stage PD residue, and this is the error of the first stage PD solution. We know that the frequency of the higher stage solution should be close to the frequency of the residue. And using this second equation, we can estimate the magnitude of epsilon1, which is the magnitude of the higher stage solution. So now we have all the information needed to optimize the second neural network. And here we just we're showing that this works very well. So the prediction from the second stage neural network agrees very well with the expected result. And again, here the error is not provided as the training data because the neural network doesn't see the data when training. The neural network can only predict the solution because it's solving the PD for the second stage neural network. So, and here just show after 2 stages, the multi-stage solution has an error that's close to 10 to the minus 13. And after more stages, the solution can be, the error of the solution can approach 10 to the power of 16, which is close to machine precision of double floating points. Okay, so this is just a quick summary. Previously, for a regression problem, the training data for higher stages come from the error of the previous stage, and that can be calculated from the ground truth target function. For PIN, the ground truth is not available for calculating the error. However, the PD residue from the previous stage neural network can be used to estimate the magnitude and frequency of the higher stage PD solution. And the PD of the higher stage neural network can be written in terms of the PD residue of the previous stage neural network. So we have all the information we need from previous stage to train the next stage and perform multi-stage training for physics-informed neural network. Again, all this procedure can be automated. Okay, so this is just to show the scaling of the error. Here, you can even enhance the algorithm by adding the gradient of the residue in the loss function term. It's also called GPINNs. So here, if you look at the throughout subsequent stages, the error of the solution compared to the dominant frequency of the error, you can see it also follows the power law. For regression problem, we saw the power has like 1/6 exponent. Here, with the addition of PD loss in the cost function, we have a steeper slope. So it's about close to 1/8. Okay, so that was for PIN with 1D with ODE, and here is a simple PDE example, right? So here we have a diffusion equation like this, where we also have an analytical solution. And here you can see the first stage PIN error is about 10 to the power of -4. After 3 stages, the error can be pushed down to 10 to the -9. And this is just to show the same scaling law of the error of the solution versus the dominant frequency of the errors. Okay, so this is the introduction of how this multi-stage high precision neural network work. And so what can this, all the example I showed so far are the example where we already have analytical solutions. So in practice, what can we use this high precision neural network for? And here I want to show an example where it can be used to solve some very challenging PDE. So it can actually be used to find some PDE solutions that are otherwise quite difficult to find with classical methods. As an example, so I'll talk about the Navier-Stokes equation. Navier-Stokes equation is widely used in various applications in science and engineering, right, for more than 2 centuries. It's also my favorite equations in the world because of its universality. However, there are also many unsolved questions concerning the fundamental behavior of the Navier-Stokes equation. In particular, we do not know if the Navier-Stokes equation always exists a solution that always exists a solution for any smooth bound initial condition. So one of the pathway to tackle this problem is to find a solution to the Navier-Stokes equation that can blow up at finite time. If one can find this example, that would be a counter example of the statement that Navier-Stokes equation always exists a unique and smooth solution at any times. So here we want to see if our high precision multi-stage neural network can be used to find blowout solutions. This question, this open question are also very important for not only for Navier-Stokes, but also the Euler's equation. Let's go back. So for Euler's equation, this will be the focus of the next few slides. And this work was also recently published in Physical Review Letters. Okay, so this is the Euler's equation. It's simply the Navier-Stokes equation with zero viscosity. An open question for this equation that remains unsolved for over a century is whether a smooth and finite energy initial condition can blow up in finite time. In the past decades, there has been several progress made by direct numerical simulations, and that suggest singularity formation for the Euler's equation. However, you can imagine that near the time of blowing up, near the time of singularity, the time and space resolution needed to resolve the dynamics are extremely high. So you need really fine resolution to resolve the singularity. The smallest length scale and the largest scale can span over more than 12 orders of magnitude. So this is this posed a multi-scale numerical challenge to this problem. And in the next few slides, I will show how we can tackle this problem with a multi-stage physics-informed neural network. So we first reduce the dimensionality. So we are working in a self-similar domain. And here we use a physics-informed neural network to approximate 4 parameters we want to solve for as a function of 2 self-similar input coordinate. So throughout the training iterations, the algorithm will search for the 4 solution profiles that satisfy the self-similar Euler's equation. And I want to emphasize that this is not a forward problem, because in this set of equation, we have a critical unknown parameter. We have a lambda parameter in this set of equations. So the search for the solution along with this unknown parameter is an inverse problem instead of a forward problem. And I will skip a lot of numerical details here. These are documented in the supplementary material of our paper. But our neural network can, so you see that is again, so this is a loss versus iteration, and the convergence of the neural network approximation of the solution over iterations. So our neural network can numerically find a set of approximate smooth self-similar solutions that exhibit singularities to the Euler's equation. And this is one of the examples where neural network has found PDE solutions that had not been found before with other more classical methods. Here you can calculate the accuracy of a solution by substitute the neural network solution into the PDE and look at the PDE residues. So this Quantum Magazine article, they did a good job explaining the background of this problem and our progress. And Charles Pfefferman, he's not directly involved in this work. He's the author of the statement of existence and smoothness of the Navier-Stokes equation. So he mentioned in the quantum article that our result is quantitative and is precise and has a good chance of being made rigorous. So this is very exciting to us because this is a possible strategy to tackle various blow-up problem where the classical simulation is difficult. Okay, so just want to sum up by saying that there has been several challenges in this general area of high precision learning. And there are also a lot of progress that's been made. From different angles, for example, there's many work that focus on how to enhance the function approximation error. And there are also paper that tackles how to do faster optimization, like second order optimization methods. I think Marius is actually giving a talk in this seminar series next week. Look forward to that. And there's also how to approximate high frequency functions. We already mentioned this paper previously. For in the context of PIN, there's various work that discuss how to determine how to weight different terms in the loss function. And the overall goal here is to make the convergence rate for different terms in the loss function roughly comparable. And there's also some work focused on how to have a strategy that optimize the sampling of collocation point, and how do you choose optimal activation functions of neural network. Finally, there are also this work by Mishra that look at, in addition, whether we can say something about the error bound of the solution based on the PD residue. Okay, so I'll encourage you to check out all of these papers. And to sum up this talk, we show that multi-stage neural network can boost approximation accuracy. It can tackle spectral bias and enhance the neural network precision to machine precision. It takes less computational cost than a single neural network. And this is useful for representing flow that exhibit multiscale features. We have also applied it to find blow-up solutions to Euler, and this is a challenging multiscale problem. In the future, we're interested in systematic study of the use of these for various types of PDEs. And we also want to see if we can use this to improve surrogate model. So how can this, very precise neural network how can it be used to help to mitigate the error and instabilities in the machine learning based emulators? And yeah, so finally, I want to thank my wonderful group members. Yangju Wang is really the core developer of the deep learning algorithm. None of the result would be possible without him. And Jenkin and Charlie are my students who contributed substantially to the deep learning algorithms. Our code, so many people ask me about the code, and it is open source available. If you want to try it, you can go to this link, and I'll be very happy to answer any questions.
Thank you.
Stop here.
Thank you so much for the wonderful talk, Yao. That was very informal, and I'm sure everyone here learns a lot. Okay, let's have a Q&A session. I don't see any questions in the chat room. So if you have questions, please unmute yourself, ask questions. Don't be shy. Oh, yes. Lucas just asked the questions. He said, thanks a lot for the presentation. It was very clear and informative. Where can we find the slides of the presentations? Okay, we are going to make this video, like the recorded video, available in the YouTube. You can check it there. Or Yao, do you mind share your slides to audience directly?
Yeah.
Or
what would be the best way to do that?
you can forward that to me, and then
Yeah, I can. Yeah, I'll forward to you the slides. No problem.
Yeah. All right. Thank you for the question, Lucas.
Hi, this is Jerome Solberg. Thank you for the presentation. I was just struck a little bit by the fact that there's a relationship, it seems, between doing the second level neural network and maybe the norm that you're using for the error, right? If you maybe used for the PD, it's natural to use like the H1 norm, so to include like the gradients in the error. So I was just wondering if you had some thoughts on that.
So I couldn't hear exactly every word.
Let me try it again. Can you hear me now?
Yeah, there's echoes, but
oh, yeah. So I was just thinking that there's a relationship between what you're doing and like the choice of the norm you use for measuring the error. And like in the PDE case, at least it's would be natural to use like the H1 norm. So you would include the gradients, the difference in the gradients and the in the error, which would naturally tend to grab a lot more of the high frequency terms. So I just wondered if you had thought about that, and if there was a relationship there that you had explored.
yeah, you're talking about how to report errors, right? And
yeah, because that how you decide on the error like determines how the thing is trained, right?
the error the training is using L2. Actually, sometimes we use LP. And our way of that is a good question. Yeah, we can look
So
at.
if you used L, the H1 norm, which is like the square of the error plus the square of the error in the gradients, then you would naturally, which is the natural one that we use for like PDEs, for like second order PDEs, would tend to capture a lot of the error that just using the L2 norm would miss, right?
I think this is a good suggestion. Yeah, we can definitely we can definitely calculate the H1 error without problem. Yeah. So yeah, I will be curious to see.
What I'm trying to say is there a relationship between doing that sort of second level of neural networks and including, say, higher order terms in the error metric. But both of them are attempting to train towards something that captures higher frequency terms more.
Yeah, that's a good suggestion. We have not really as calculate H1 error so far. Is still ongoing work, and we're just really looking at a simple difference between. But yeah, I see your point. I think it's a good thing to do. We can definitely report errors. Yeah.
Thank you. Robert, I know you put the question in the chat room, but do you want to unmute yourself and then ask?
Yeah, sure. So you mentioned at the start of your talk, maybe we can talk after, you wanting to investigate why you're seeing that alpha coefficient appearing over and over again with your graphs. Have you looked into any of the research on the empirical scaling laws of neural networks?
Yeah. So the empirical deep scaling convergence laws, and that's
Yeah.
what can you remember what's the alpha value there, or is
So interestingly, the alpha values there seem to work something like a condition number, an analog for like mathematical problems, in that they are constant for the problem being discussed, but are independent of the network architecture used. But only sometimes there's like research that shows that LSTMs and transformers, for example, have a fourfold difference in their coefficients.
interesting. Yeah. I think here I think this is something I'm really curious to see, because in our case it's actually quite consistent with what we see, that the independence of the architecture and the depth and width, but the
I've been looking at it for a while. It's like, you know, we can talk afterwards, but basically the other questions I had, I just wanted to kind of alert you into that because I think there's a connection to what you're doing there. And I also like wanted to ask, do you have any insights about how the size of the network affects the frequency response of your networks? If I say add 1,000 times more parameters to my network, can it capture more spectral modes?
I really like this question because I had that exact same question like a year ago. Like if we draw an analogy to a Fourier series, right, you would think that more terms you would be able to capture like a broader range of frequencies. Interestingly, if let's do a simple test, a simple thought experiment. If we just have one single hidden layer and then replace all the activation function by signs, so it's like close to like a Fourier series, and then you ask the question: can increasing number of neurons increase the ability for the neural network to capture higher frequency data? The answer is actually no, because that depends on how you initialize the neural network and the optimization procedure. It's really the architecture itself is fine, but it's the way neural network learn how to optimize parameters that's like limiting its representation accuracy. So that's why in our case we initially just increase the depth and width, and that has like, I think you will also see a scaling law actually, right? But the exponent is not as large as 6. It's not as large.
The scalings are usually really, really poor. Like I wonder, and this actually brings into the reason I asked the third question there is, how do you apply this idea to a problem where you can't really do a frequency analysis? Like, say I wanted to take and do a multi-stage neural network for something like an LLM. How could I do that without being able to analyze the kappa?
Let's see. That's a very good question. So if you
Yes,
have,
I think what the LLMs are seeing are basically the same phenomena that you are seeing on these physics problems, right? They have some problem, and you read the studies on how things suddenly grok. Like it really sounds to me for someone who has a physics basis, as in they've suddenly discovered a frequency mode of the underlying data. And you look at these networks a lot, like they usually smooth over noise until they suddenly find a signal in the noise, which could be like analogous to suddenly finding the frequency in a feature space where this all suddenly makes sense. But it'd be really interesting, and we have lots of problems around here where I'd love to apply a technique like this. I've spent 2 years trying to fit a network to machine precision or something and failing, and like no one has been able to find a network that can reason down. So I'm really excited by this, but we have problems where you can't do a frequency analysis to find what the dominant frequency is.
I'm very interested in and intrigued by your question. So in the LLM, then the question is, what does it mean when a neural network is of low precision?
Yeah.
Right? Like, is it also fitting some what does it mean? What's the part it's not fitting?
Yeah.
I don't know the answer. I'm just curious. Yeah. So we can talk more.
Okay.
Offline.
All right. Thank you for the question and answer. That's wonderful. Any other questions from audience? I think William, you raised a hand one time, and if you're still there.
Yeah, I guess it was kind of somewhat related to what you were talking about. I was curious if when you're implementing it, if you needed to go through and tune each autoencoder architecture as you're going through and adding these extra levels. But it sounds like if you just feed in the data, the architecture doesn't matter. If you feed in the errors, the actual architecture doesn't matter that much. It's just what you're training on.
Exactly. There's the only thing that we have to decide, because all the parameters like the scaling factor that tune the weight of the neural network of the higher stage neural network, those can be determined just from the result of previous stage. So those are not really the tuning parameter. But one thing we do have to decide is when to stop the training of a particular stage. So that is still we kind of decide manually. It would be really good to have a way to automate that process. I don't know if that answer.
Yeah, definitely. Thank you.
I have one question. For the multi-stage pins, you have to provide some collocation points as well. Do you see, your multi-stage pins convergence behavior depending on the number of collocations and position, the location of the collocation points as well? Have you probably you have done some
This
study on
is
that?
this is actually a very important question. So if we actually for the pin case, we have done something almost similar to the regression problem. The first thing we try is increasing the collocation point, and we see that the error doesn't really come, like error goes down, but there's a limit of the error of this of the PDE solution. So then we know then that's when we know the limitation of the error is no longer coming from collocation point.
Collocation points.
It's the architect. It's the optimization of the network. It's like not learning these high frequency features. So then when we add the second stage network, we have to still do the same experiment. We have to make sure we have enough collocation points. So it's not limited. The accuracy is not limited by the number of collocation points. It's limited by the optimization of the weight and bias.
Oh, so you're not using the same collocation point sets from the previous stage. You always go back and then try to find out the what is the enough, like the necessary number of collocation each.
They don't
each
have to be the
stage.
same. They don't have to be the same. But I think it's easier if you just use the highest density of points. It's a little bit like the regression problem. The downside is that it increases the computational time. If you just use the highest possible collision point density in the beginning. So in the beginning, you can use less. In the higher stage, you need to use more points.
Right.
I think for regular problem is really not. It's really too expensive to do this. It's really for this special type of PD. You really need high precision, and then inverse problem where deriving a joint for this couple of nonlinearity is challenging. That's the type of problem where I see it's beneficial.
Right. I'm just curious. The pins usually takes a long time to, get the converged solutions. How about your multi-stage pins? Any benefit of accelerating that training at all?
So depend on what you meant by accelerate. If you ask for the same precision, what's the computational time compared to the regular pin? The answer is yes, it's faster.
Right.
Yeah, but
if you compare that with a traditional PDE solver,
then is definitely not. Like I wouldn't recommend using this to solve, for example, like diffusion equation. That was like for showing how this work, like a simple example where you have analytical solution.
Right. All right. Oh, thank you. The robot, you seems to have another questions.
I have like 18 questions, so that's fine.
Just one more, okay?
Well, so like the last question I have there is what happens? Have you ever had the network predict the kappa figure for you during training of the residual?
I think it is kind of being predicted by the neural network because the kappa is determined from the outcome of the previous stage. Like usually
if the network could predict the kappa, like if I'm training the first residual network and then the second residual, if they're each picking their own kappa, that would offer a way for you to apply this to problems where there isn't a clear Fourier analysis analog, because in those situations you can't calculate that explicitly, but if the network could find it during its own training, that would give a mechanism for this to have way more generalizability to a whole host of different problems.
I see. That's a really, really good point. It can, I think, so this depends on, I think it's related to the question of the scaling law. Because the scaling law actually gives you can track down the scaling law and then find out what's the kappa for the error. So then if you know the error of the first network, you can kind of estimate the kappa.
Yeah, that's a really good point. Like, this is such a cool idea. Okay.
Yeah, but I still don't, I don't know how universe, like a question I'm really interested in is why is there a scaling law for this? Like, why is it 1/6? Like, we have empirically show if, like, is it like how universal is it? When does it break down, right? This kind of question I'm very interested in.
I'm extremely interested in this. Well, the empirical scaling laws and the fact that these coefficients keep appearing over and over again is driving me crazy, and I'm glad that at least someone with a mathematical background is looking at it.
I would like to chat more. Yeah,
Yeah.
touch.
I mean, my follow-on questions to those discussions between you would be, even though those kappa value can be induced from the previous training by looking at the residual, dynamics, and therefore we can apply that to the problems where the Fourier analysis is not available. But still, LLM, I don't see how it is applicable to there.
So
What does it?
there's research that shows that they can do like mathematical analysis backing out stuff in LLMs, and they can show that at least English seems to work on a 42-dimensional manifold that we don't understand, but they can do like analysis of convergence laws and various stuff to show that, hey, like there is like a 42-dimensional space that thought seems to occur in. And with doing vector operations in that space, you can do stuff too. So like we can't understand it, but there is a high dimensional space where like an FFT should apply. We don't know what it is, and the networks can't approximate it well. But like all these ideas should apply to those spaces as well. Like I think that again, I wrote it in the chat. Like I've tried for a while to get networks to do a convergence thing like you're describing, and I've never been able to get it to work, just kind of on the side while I'm doing other things. I really think the frequency analysis is very, very key to finally getting like a spectral and multi-scale type thing working here. I think that is the key thing is you've added something to the network that allows you to capture different modes explicitly. And that is what is making the whole process work. And that's what is giving you convergence factors, those scaling factors that are factors of 10 bigger than anything else I've seen when I'm looking at convergence stuff elsewhere in literature.
Well, I mean, that's a cool idea of, those English, for example, it can be embedded into the 42-dimensional vector space, but I still don't see how that can be used to, provide some residual information, so unless there is some sort of governing equations to, guide those residual
Oh yeah, of course.
computations.
Well, the first example did like they showed example in the beginning where you get able to do it without having the governing residual equations. You can just look at the residuals for the problem, and we have those for things like L stands. So I mean, we have those for every problem. So there's a general result from the thing. So even though we don't have the governing equations,
The data, actual
we can
data.
still apply it directly from the data.
Right. Okay. Cool. Any other questions? It's past the time, unfortunately. I'm sure many exciting questions will come up, but we have to wrap up soon. So maybe one more question we can take. Well, if not, let's thank our speaker, Yao, for the wonderful talk and wonderful Q&A sessions. And I'm sure that many people is going to be interested in your work, Yao, and future collaborations hopefully comes out, initiated by this seminar.
Yeah, thank you, Yongshu, and thank you, Robert, for the points about LLM. I'm very interested. I need to learn more about it. So
Awesome.
okay.
All right. Well, thank you.
Yeah.
With that, we conclude the talk.
Yeah.
The
Thank
seminar.
you. See you. Bye.